Hi guys! So this video is going to be discussing variational autoencoders, and this is not part of the Data Everyday series. I'm just doing this because it's a really cool deep learning application. It doesn't exactly have so much practical significance, it's not very useful, but it's really interesting. So I thought we'd take a look using the age, gender, and ethnicity face data CSV dataset. So what we're going to basically do is try to create a generative model that can create images of faces based on, well, I'll explain the workings of the variational autoencoder as we go. So this is the basic structure of an autoencoder, and basically the way it works is you have the input and you ask the model to recreate the input as the output. So the labels here, the target that you're comparing the output to is the input again. So what you're encouraging the model to figure out how to recreate the input. However, we enforce an information bottleneck on the model, which means the dimension of the information that can be passed through is lower than the original input. So we're going to lose some amount of information as we pass through the model. And so what this does is encourages the model to store as much useful information into, let's say, 3 values like this. It tries to encode as much useful information into these 3 values as possible so that it can use those 3 values to recreate the original image to a high degree of precision. So what this has the effect of doing is afterwards you end up with sort of 2 models. The encoder, which is this part before the, we'll call this the latent representation. The reason we use latent is because we're sort of hoping to capture real-life variables that created the original features. So if that's a little confusing, what I mean is these variables are more meaningful than any of the original inputs. So we're trying to sort of reconstruct the variables that created the original inputs. So we call them latent variables, or a latent representation. But basically, the encoder is responsible for creating this latent representation, and it's creating a representation that is most useful for reconstructing the output. And that's what the decoder does. The decoder will take a latent representation and reconstruct an image, in our case, based on that. So we're going to see how this can be used, and we're going to visualize it with a cool interactive widget that will hopefully demonstrate some of the intuition behind this. So this is an autoencoder. Now a variational autoencoder is slightly different. It's very much the same idea, except instead of directly learning the latent representation, we learn a mean and variance to pass into a probability distribution from which we sample the latent representation. And this provides some more flexibility in how we can, in what kind of distribution the latent variables can come from. So a variational autoencoder is like an extension of the original autoencoder. Alright, so let's import some libraries. We're using NumPy, Pandas, and PyPlot for working with and visualizing the data. We're going to train the variational autoencoder with TensorFlow and construct some widgets with IPy and the display function from IPython. Let's go ahead and import that. And first thing we'll do, I guess, is load in the data. We want the data in the environment so that we can work with it. So I want to get the CSV file here. Let's call it data. Pandas.readCSV, pass it in, take a look. Now this file, I think we look, oh yeah, we can just see it here. We have the actual pixel values as a column in a data frame. So we're not working with image files, but all the image data is encoded here. These pixel values will take values between 0 and 255. Alright, so this is this is an unsupervised learning task. Because we don't need label data. In fact, all we're going to need here is the pixel data. So what we'll do, let's actually just load in the pixel column. So I'll say subpixels. So data is just going to be the pixel column as a series. And then we're going to take that series and turn it into a NumPy array. So, okay. Let's sample it first. I want to shuffle it just so we can. So we'll do data.sample, sampling 100% of the data, so fraction equals 1.0. Give it a random state so we can reproduce the results. And after we sample it, so I'll just say shuffle the data. Then let's convert the data into a NumPy array. So we're going to take the data and apply a function, lambda function, that for every x here being one of these rows, we're going to turn x into x.split on white space. So that will give us a list of all the numbers. And we're going to turn that list into a NumPy array with a data type of numpy.integer. So now if we run this, we look at data. Data should be a NumPy array. This might take a moment actually. But actually, I'm not sure the shape will be right. If we look at data.shape after, I'm pretty sure it's going to be a NumPy array of lists. Oh. Hold on. Right, this is a series of NumPy arrays. So what we're going to do then is we'll turn the actual series into a NumPy array, like that, and then what that will turn into is actually a NumPy array of NumPy arrays instead of it just being one NumPy array. So we can fix that by stacking it. NumPy.stack along axis 0. This way. So after this is done, we'll say let's rescale inputs, pixel values, to be between 0 and 1, which is standard when we're inputting it into a model. So we'll take data and just divide by 1 over 255. So we can say data equals data times multiply by 1 over 255. Like that. Alright, so we'll run this, and now data should be a NumPy array with values between 0 and 1. And it should be 23,705 images by however many pixels there are here. So I'll run this. As soon as that finishes, it should show up. Alright, so that looks right. The shape is, okay, so we have 2304 pixels. If we take the square root of that, of 2304, that's 48. So this is a 48 by 48 image, and there's 23,000 of them. Okay, so now let's do the modeling. Building the VAE. So, okay. Essentially, I guess we can make this a function. Call it build VAE. And we want to pass in a number of pixels and the number of latent variables. I'll default that to 3, because we'll use 3 today. Basically, the number of latent variables is the dimension of our latent representation. So how many of these values do we have? The higher this number is, the more information you can encode in the latent representation, and the better the reconstruction of the image will be. However, as you increase the number of the latent variables, you also lose an understanding of what each one does because there's more of them. So like I said, there's not really much practical application for VAEs. They have been used on occasion for practical applications, but in general they're more just for educational, motivational purposes. So understanding the meaning behind them is really just for our own convenience. This doesn't really have much practical significance. Okay, so we're going to break the model down into two parts, the encoder and decoder. So for the encoder, we're going to pass in the image. And I'm going to pass it in as a single vector of 2304 pixels, so I'm not going to pass it in as a two-dimensional image. We're not using convolutional layers here, just dense layers. It's really just dense layers until we get to the bottleneck, and then dense layers back up. So we'll call this encoder inputs, and this is just going to be tf.keras.input. The shape here will be a vector of length 2304, but that's the same as num pixels, so I'll just pass that in here. Then we'll just have some dense layers. So this, the size of these is really up to you, as long as it sort of cascades down towards the latent representation. You want progressively more information loss as you approach the latent representation. So this will be dense, layers.dense. And since we have 2304 to start with, let's bring it down to 512 on the first layer with a ReLU activation. And we'll pass in encoder inputs. Then we'll replicate this twice, and I'll make it cascade down to 128, and then 128, and then again to 32, and then finally this will be x. This will be x and x. Then finally, we're going to encode the latent representation. So we usually call this z. So z will be our latent representation. And if we were doing a typical autoencoder, we would just run it like this, and this would be our number of latent variables. So let's say 3. And these 3 values, actually no activation, with a linear activation here. This is how we would create the latent representation for a regular autoencoder, not variational. So the decoder, we'll come back to the variational aspect in a moment. Let's do the decoder. So the decoder's inputs is going to be another input. So let's change 3 to num latent variables, which by default is 3. So the shape of this input is the shape of num latent variables, because we're feeding this into this. We're feeding the z into here. So right over right. So okay. All right. So after that, we sort of build the decoder up and in a symmetric fashion. So let's take this. This is going to take in decoder inputs, and we're going to copy this over twice. This one becomes 128. This one becomes 512. And you can see it cascades down towards just the latent representation, and then up again back towards the original image. This should be x and x. Alright, and then we'll create our reconstruction. So this is the output of the decoder, and it's a reconstruction of the original image. So that will be a dense layer with num pixels as the number of neurons it has. And this will have a linear activation as well, because we don't want to change the values in here. We want them to take any value. Alright, so here we pass in x, and then let's create the models. So over here we'll have our encoder. Just do that. The encoder is going to be a model, a Keras model, where the inputs are encoder inputs. Whoops. Okay. And the outputs are z. Now the decoder is going to be a Keras model. The inputs are going to be decoder inputs, and the outputs are going to be the reconstruction. So these need to be joined up together. So let's create the full model, which is going to be, we'll have model inputs, which will be the encoder dot input. So that's the input of our encoder model, and our outputs, which will be decoder dot output. Actually, that's not true. Okay, so we haven't linked them up yet. Right now these are two separate models. So to get the model outputs, we want to pass the encoder's output into the decoder and then get the output from that. So what we do is take the encoder dot output, which is the result here, z, and pass that into the decoder. So then this will spit out the output from the decoder, which is the reconstruction. Then we'll create the model, which is tf.keras.model, where the inputs are equal to the model inputs, and the outputs are equal to the model outputs. Alright, then what we'll do is compile and return the model. So model.compile, we'll give this an atom optimizer. The loss function here will be MSE. Since we're comparing the reconstruction to the actual image, pixel by pixel, so we're just trying to minimize the square difference between those pixels, one at a time. And then we'll return all three models. So let's return the encoder, the decoder, and the model. Alright, and this looks like a good function. So let's try this out. Let's build one. So what we'll say is, well, why don't we call this face encoder, face decoder, and face model, as we're using face images here. And we'll call the build VAE function the number of pixels here, I believe it was 2304, and the number of latent variables will be 3. So if we run this and we look at our face encoder.summary, you can see this is just a neural network that takes in the pixels and brings it down to just 3 values, outputs 3 values. That's our z. Why don't we name this one z so we know? Alright, so here's our z, which is our output. And then let's do the same thing for the decoder. You can see this takes that z and rebuilds the original pixel, the original image. So our full model, which is face model, okay, it's counting it as a functional layer, but really this is the decoder. So it creates the latent representation and then uses the decoder to reconstruct the original image. Alright. So now let's implement the variational aspect of the model. So if you recall from before, the variational autoencoder differs in that it we, instead of learning z directly, we learn a mean and variance to use in a probability distribution from which we will sample z. So by default, this is used with a Gaussian distribution, normal distribution, where you just learn mean mu and variance sigma squared. And then we sample from that distribution with that mean and variance, and then use that sample as our z. So let's do that here. Now, we need to build a custom layer for this. So let's create our custom layer, which will be called a sampling layer. And this code is going to be taken right from Keras' website, which will be inheriting from tf.keras.layers.layer. And we just have to implement the call function, which takes in some input. So this is the feed forward function. So the inputs here is going to be, instead of z, let's go ahead and change this. So our z, let's erase this. Z is now going to be coming from our sampling layer. And we pass into the sampling layer a vector containing the mean of z and the variance of z. Now to get the mean and variance of z, the mean is going to come directly from a dense layer, from X, and we're getting the dimension of the mean is going to be the number of latent variables, because we're getting a mean for each latent variable. So that, yeah, and no activation here. Then the variance is actually coming from the mean, and that's because the mean is used in the calculation. This also has size, or dimension of number of latent variables, and we pass in z mean. Okay, so let's take note of this function. tf.keras, tf.keras.backend.randomNormal. What this will do is generate, we need a shape. Let's just generate one. This will generate a single value drawn from a normal distribution with mean 0 and variance 1. Now, there's a bit of an implementational trick here, where instead of drawing the value directly from a normal distribution with mean and variance that we specify, if we did that, it would be difficult, impossible actually, to back propagate through the network when we do the model updates. So instead what we do is we draw the value, we draw a single value, we'll call it epsilon, from a normal distribution with mean 0 and variance 1, and then apply a shift and scale based on our mean and variance that we get from the model. So if you draw a value from standard normal, which is mean 0, variance 1, and then shift and scale that, it's essentially the same as drawing it from the original distribution with the mean and variance that you specify. So what we're going to do is, instead of having this shape, instead of just drawing one, we're going to specify a batch size and the dimension, which will be the number of latent variables. And what that will do is create 3 epsilons, one for each latent variable, and one of those for each batch. And so each of these is going to be shifted and scaled by our mean and variance for a given example and a given latent variable. So let me simplify this. Okay. So there is one more sort of implementational trick. Instead of getting the variance directly, we're actually going to get the log of the variance, because if you take a look at the log function, this is something that seems pretty intuitive, but I feel like is not usually talked about in a great way. If you take the log function, what log is basically doing, log transform, it's sort of matching up the small infinity to the big infinity and putting them on the same scale. So you can think of 1 as a cutoff point, no matter what the base of your log base e, that's the same as a natural log. That means it doesn't matter what this is. You could have base 2, it's always 1. Base 10. But after 1, we have the big infinity. And by big infinity, I mean countable infinity, or infinity approaching really big numbers. So you can see this infinity just goes. We're talking along the x-axis here. This will go up larger and larger numbers. On the other hand, we have the small infinity, which is getting closer and closer and closer to 0. So this would be uncountable infinity. And what the log function does is it takes the big infinity and the small infinity and puts them on an even scale, the y-axis here. So on the y-axis, the positive numbers on the y-axis are what the big infinity is mapped to, and the negative numbers on the y-axis are what the small infinity is mapped to. So what we end up with is seeing orders of magnitude on both the big infinity and the small infinity represented in an evenly spaced line. So what I mean 1 is the cutoff point in the middle. 10 would be next, since we're doing in base 10. And you'll see 10 is 1. So if we move one step up, one integer up, we get one order of magnitude higher. If we move 2 steps up, which should be up at 100, right there, we get 2 orders of magnitude higher. On the other hand, if we move one step down, we get one order of magnitude lower, so that's divide by 10. This one's multiply by 10. And if we move 2 steps down, we get 2 orders of magnitude lower, which is 0.01. So let's divide by 10 twice. Going up, it's multiplied by 10 at each step. So maybe this improves your understanding and intuition of the log function. The reason this is useful is because when in programming languages, numbers that are really close to 0 tend to be numerically unstable. So it helps to apply a log transform to set all of those numbers onto a much nicer, broader scale. So we are doing that just to improve the efficiency of the computation. Alright, so let's change this as well. That's log variance. And alright, let's go back up to our sampling layer. So we're going to take, we're passing in the mean and the log variance. That's going to be inputs. So let's just redefine those in here. We'll create these local variables that just come from, where is it? Here. So we're passing them in, and that's coming in as inputs. So let's just rename them in some nice local variables. That's all that's doing. Then we'll create the size of our batch, which these are already coming in as a batch by dimension. So the batch is just going to be, well, you can use tf.shape to use a TensorFlow function to get the first dimension shape of the shape of the mean. And the dimension, which is the number of latent variables, will be given by tf.shape of the second dimension of the mean. Right, so a z-mean is coming in from this dense layer. So the shape of z-mean, if we were to run this, that'll give us the indent problem. Let's just real quick jump this back, run this like that. Ugh. Okay, okay, let me just quickly, whatever, okay. Let's copy this then. I want to show you this. Bring it all back, just change num pixels to 2304, and num latent variables to 3. Oh yeah, and we don't need that. Alright, so z-mean. The shape of z-mean is going to be the batch size during training, that will be defined, by the number of latent variables. So this is what's coming in as z-mean. So we have 3 means, one for each latent variable, and the log variance is the same. They both have batch size by number of latent variables. So over here, what we're doing is just giving those their own names, batch and dimension. And now we're going to draw the epsilon from our random normal. So that's what this is. Epsilon is going to be a NumPy array or a TensorFlow tensor containing 3 epsilons for each example in the batch. So we have batch size by number of latent variables, epsilons. So let's call this epsilon. And that's going to be tf.keras.backend.randomNormal. The shape here is batch by dimension. Alright, so now we don't just want to return epsilon. We've now drawn our epsilon, which is just drawn from the standard normal with mean 0 and variance 1. So we want to return an epsilon that has been shifted and scaled by our mean and variance. So epsilon right now has nothing to do with our mean and variance. So now let's do the shift and scale of the epsilon. So we're going to multiply epsilon by some value to scale it, and then add some value to it to shift it. So I guess we can just add the value first. We're just shifting by the mean. That will give epsilon the effect of having been sampled from a normal distribution with the mean we specify. And then we have to scale epsilon by some value. And we can't just scale by z log variance, because log variance is not. We actually have to scale by the standard deviation, which is going to be the square root of the variance and not the log variance. So let's just take a look here. Essentially, okay, so our variance is, sigma squared. Okay, so this is the variance term, and what we want to do is scale by sigma. However, we don't have sigma squared, we have log of sigma squared. So how do we turn log of sigma squared into sigma? Well, what we can do is take e to the ln of sigma squared, which is equal to, it's equal to e to the ln, okay, wait, hold on. We don't want to do this yet. What we want to do is square root. Wait, give me 1 second. Let me just figure this out. Okay, yeah. So we have log sigma squared, which is our log variance, and we want to get sigma. So we can do e to the ln of, this is our log variance, times 1/2. So this function should give us sigma, because if you look, just scroll down, this will simplify what we can do, because multiplication for exponents will give us this, e to the ln of sigma squared, that whole thing to the 1/2. Since you multiply the exponents, it comes out. And then this inner term will be simplified, because it's e to the ln will just become sigma squared to the 1/2. And then 1/2 is the same as square root of sigma squared, which comes down to just be sigma. So this is the transform we want to apply right here. Make that red. So let's do that in our function. So we want to take, we want to raise, actually let's use this one right here. We want to raise e to the log variance time log variance divided by 2. So what we'll do is divide the log variance by 2, and then raise, we'll take e to that value. So over here, we have our log variance. Let's divide it by 2, or I'll multiply by 1/2, or I guess by 0.5. So we have 0.5 times log variance, and then e to that power. So that's tf.exponent to the log variance times 0.5. Alright, so then we scale epsilon by this value to get the sigma. So this is our sigma right here, our standard deviation. So we're scaling epsilon by the standard deviation and shifting by the mean. And so this should have the output of returning us an epsilon that has been drawn from a probability distribution, a normal distribution, with the mean and variance that we specified. So again, we're not drawing directly from that kind of distribution because of the backpropagation issue. So we draw from a standard distribution and then shift and scale based on mean and variance. So let's run that. And now we can use our sampling layer over here. If we look at z, you can see z now is 3 values for a given example. And these 3 values will be our latent variables that have come from our standard normal, and then shifted and scaled by the standard deviation and mean. So these are our latent variables. This is our z. And so we now have the variational autoencoder working for us. Okay. So let's, I think this should work. Delete this. Run this, and then look at faceEncoder.summary. Alright, so you can see we're using a sampling layer to create our z. Alright. And you can see this is taking input from both our mean and variance layers. Alright, so let's train it. It's enough theory. Let's actually train the model. So let's do this down here. I'll keep it there. Alright. So let's call it history. That's going to be from face model. We're training the whole face model. Now when we train face model, the weights within encoder and decoder will also be affected, so we can access them after it's been trained. .fit. The data here is just data, and the label data, the target data that we're comparing it to is also data. So we have data at the beginning and data at the end. And this is the pixel. Let me call it pixel data actually, so it's not confusing. And I'll just go up here and call this pixel data. Oh, and that's pixel data. Alright, so then we'll just give it a validation split so we know when to stop the training, 20%. Batch size, this can be 32. We'll train for 100 epochs and use this early stopping callback function, which is tf.keras.callbacks.early stopping. And we're going to monitor the validation loss. And when it stops improving after 3 epochs, we will stop the training and restore the weights from the best epoch. Alright, so let's train it. And there you can go, the loss is going down. And what this is doing now is finding 3 values that can reconstruct the image. That would be finding 3 values is the encoder part, that can reconstruct the image is the decoder part. And it's doing it all in one go. So when this finishes, the first thing we'll do is try to reconstruct an image to see how it's doing. And so this is the cool part. We're about to see what this is really capable of. So what we'll do is create a sample. This will just be a single image from our pixel data. So we'll just take our pixel data. We'll take the ith value in there and create a copy of it and make that our sample. And we'll reshape the sample so it's an actual image that we can visualize. So sample.reshape, and this was 48 by 48 image. So we'll take that 2304 pixels, turn it into 48 by 48, and by 1 for grayscale. These are grayscale images. Then we will create a new pie plot figure with a figure size of 10 by 5. And we'll plot side by side the original image and the reconstructed image. So we'll have 2 subplots. The first one is they're both in a 1 by 2 grid, so 1 row, 2 columns, indexed by 1 for the first one. And we'll use the imShow function from pieplot to show the sample. We'll give it a gray color map since it's grayscale. We'll turn off the axis tick marks, and we will give it a title, original image. Then we'll duplicate this. This will be indexed by 2, and this will be the reconstructed image. But instead of it being sample, what we'll do is create the reconstruction. So let's do that up here. Our reconstruction is going to come from our model.predict. I called it face model, right? And you can see it as finished training. So face model.predict on sample. No, we can't use sample. We'll do face. We'll do pixel data sub I dot copy, like this. And then let's reshape the construction as reconstruction as well. So reconstruction dot reshape equals equals reconstruction. Whoops. All right. And I. Oh yeah, we need an I. So let's just use this the 7th image in here. So I equals 6. What is this? Oh, okay. It's because of the batches. So what we'll do is turn this into a NumPy array, because I think it's returning a TF tensor. Then take the ith example from that. Wait, does that work? Oh wait, we want to predict on the whole set of pixel data, and then take the ith prediction. Alright, and here we can see. Okay, so actually we're seeing the original image twice. We just have to go in here and change this to reconstruction. And we'll do plt.show. Now let's see how the model's doing. Alright, so not so well. I mean, it's remarkable, right? It did create a face, but it doesn't really look like the original face. However, the reconstruction in itself is not really the most remarkable part. In my opinion, the decoder is what makes this so cool. Because here, what we're doing is taking in an input, creating a latent representation, and then passing that latent representation into the decoder to create this reconstructed image. But we don't have to pass in the latent representation of an actual image. We can pass in any values for that latent representation. We can pass in any values to the decoder to get an image of a face. So this is where it gets cool. Specify our own latent variables, latent variable values. So what I'll do is create a function called generate face image. And this takes in 3 latent variables: latent 1, latent 2, and latent 3. What we'll do is just take those 3 values and combine them into a single NumPy array. We'll call it latent vars. That will be a NumPy array containing all 3 of these. Yeah, we have to convert it. We'll make it into a list, and then I think it does want it to be a list of lists. So we're going to do 2 brackets, and then all 3 latent variables. Then we'll create our reconstruction by taking our latent variables and passing it into our decoder. So face decoder of latent variables. This will return our reconstructed image. So note, if I run this and I pass in something like this, and I specify some values for this, we will get an image. So just note that this is the reconstruction. And what we'll do is reshape the reconstruction. So that would be reconstruction dot reshape. Now to be an actual image, so 48 by 48 by 1. And then we'll create a pyplot figure and use the image show function to show the reconstruction with a gray color map. We'll turn off the axis and we'll call plt.show. So let's use this function now. This should be able to create an image based on 3 values we specify. No. Oh, okay. Let's turn this into a NumPy array then. Like that. All right, and we got an image of a face based on some values here. So if we change these, the face will change. Make it -5. It changes drastically. Let's build an interactive widget that will allow us to modify these values with sliders. So we want sliders that will create different images. So we want to specify the min and max slider values for each of the latent variables. So let's first calculate the minimum and maximum values just by looking at the data and finding the min and max for every latent variable. So let me show you what I mean. If we take our face data, no, sorry, pixel data, and we, this is a NumPy array, right? Yeah, okay. Oh yeah, and so if we pass this in to our face encoder, that will give us a latent representation for each of the images. So now we have 3 latent variables for each image. We just want to find the min and max for each of the columns here. So we can type .numpy to get it back as a NumPy array. And then just slice, we'll say all rows, but just the first column. That will just give us back the first column only. And then we can take the numpy.min of this to get the minimum value for the first latent variable. So we'll call this latent1 min. We can do similarly latent1 max by taking the numpy.max of this. Then we can do it for latent2. The only difference here is instead of doing the first column, we do the second column. And we can do it for latent3, but the difference here is that we're using the third column. Alright. So now we'll create the widget. So we're going to create, let's call it face image generator. And this will be coming from IPyWidgets, so I called that widgets. And it has a nice widget called interact, which allows it to be continuously updated as we adjust the sliders. So the function that will be called by the sliders, the way this works is you specify a function. Our function is generate face image. And then you specify values for each of the arguments of the function. Or rather, you can specify the min and max values for those arguments. So latent1 will have a minimum of latent1 min and a maximum of latent1 max. Latent2 and latent3 will be similar. So 2 will just be like that, and 3 will just be like that. Alright, and for all this, the moment of truth is upon us. We'll call the display function from IPython and display our face image generator. And here it is. So this is remarkable. As we adjust this, we can see the image change. And we're now passing different values into the decoder, and it's creating reconstructions based on the values we pass in. And this is absolutely crazy. So it's really hard to say what these sliders represent, like at an intuitive level. But you can have some sense of it without really being able to put it into words. Just by looking at it, you can see what the slider does. It looks like this latent3 slider might almost be like changing the orientation of the face, like from left to right, as we slide it across. Either way, it's absolutely amazing, and if you want to play around with this a little more, maybe try this out with different data sets. I did this also with a digit recognition, so you could actually create different digits based on adjusting these sliders. But the face is, is the craziest one I've seen so far. And yeah, so I hope you enjoyed this video. I encourage you to hop into the notebook, try it out for yourself. But that will sum up today's video. So thank you so much for watching. I hope you enjoyed it. If you did, make sure to subscribe and hit the bell for more content, and I'll see you guys later. Have a fantastic day.